one of us go gets it, we get
Extra credit on that. All right, so we're going to write define, what did I call it? List sum. Add nums will work too. This guy's going to be a lambda that's going to take a list as a parameter. We'll have to ask the question if null. If null list, return a 0. Else add car of LST onto list sum of cooter of LST. Something like that. So if we're out of numbers to add up, go ahead and return a 0. That will finish off our final call to sum, final call to add. Otherwise, let's add the first number in the list onto another call to list sum, passing it the rest of the list. Make sense? Mistakes were made. Like little mistakes or like embarrassed your family mistakes?
I don't know that I embarrassed my I left out the if and I tried to put an empty list instead of 0.
You left out the if?
Yeah, I don't know how I left out the if, but I definitely left out the if.
So you asked no questions.
Yeah, no. Well, I mean, it has no question mark list. But,
oh, okay. So you visually acted like you were asking a question.
Yeah.
You just happened to not put the word if in front of there. But then instead of returning a numeric value, you returned an empty list. So you're doing the sum thing?
Yeah.
So you're trying to add the car of the list onto the empty list. Potentially the empty list. But all the rest of it's the same? All right, that's a 0.
Good to know.
Well, I guess it's a 30. You put your name on it.
Yeah, I did.
Yeah, it's probably more than a 30. It's like
A 40.
35, something like
Yeah, 40.
that. I'm not generous. Oh, look at those guys. Man, do you see this creepy baby? See this thing?
It reminds me of like the baby monkey dog thing.
Yeah, we're making this platformer in the 275 class, the game programming class. And this happened to be the sprite sheet I grabbed. This guy's creepy. It's going to be like a zombie baby thing.
Good to know that I have that to look forward to.
Yep. All right, so we're 121. It's the first one. 2 stars. Let's see. Product. SOS, where SOS are each lists of symbols. Okay, so these are flat lists of symbols, right? So similar to like our flat list of numbers. So a list of symbols isn't going to have more lists of lists in it, will it? Okay. Well, we could do that if you want. Let's solve it the simple way first. Actually, it should be the same because it's just another recursive call. But so a list of symbols as opposed to an S list, right? So an S list is that list of symbols that can contain other lists. So what they're getting at here is a list of symbols is similar to my list of numbers I just had in that quiz, where you have a list and it has symbols in it. Okay? No chance of having more lists in there. If you have more lists in there, not the end of the world because you would just be making duplicates of the list. So it doesn't change the logic substantially. Okay, and what are we doing? So there's no repetitions in those symbols, so you're guaranteed that you won't have XX or something like that. Return a list of 2 lists that represent the Cartesian product of the 2 lists of symbols. So for example, if we have this is a 3 list, and in this case a 2 list, they want us to return a list containing a whole bunch of 2 lists. So this is AX is one 2 list. AY is another 2 list. BX, BY, CX, CY. So for each element in this list, we want to go through every element of this list and create a 2 list. Right? Okay? So, break this down into small pieces. Let's say that we have a single symbol and a list. And I want to turn that single symbol and that list into a list of that single symbol with all the elements in it. So for instance, forget about this first thing being a list. Let's just say I have an A. And I want this A, when applied to that guy, X and Y, to be they'll give me the list AX and the list AY. So we're going to solve the simple problem first. All right. What did we decide was the comment? Semicolon? That's a comment? All right. So for example, if I have two parameters, so what's this guy supposed to be called? Product? So if I passed in product A and XY, for example, this guy should give me the list containing the list AX and the list AY. That's what the output of our simpler case is going to be. So we're not having to go through every element of this first thing. Just the first thing is its own thing. Make sense? All right. So we're going to go ahead and let's define a product that's like this. So define product to be a lambda that takes in a symbol and a list. Maybe you call it LOS, list of symbols. That's kind of like a naming convention thing. And what we want to do is we want to give ourselves a list containing, so we should have a list with the same number of elements as this, but with each element in this, having a list built with S in front of it. All right, so if LOS, if null LOS, if we're out of stuff, return our empty list, right? Okay. Else, we have stuff. What are we going to do? We're building a list, so we're going to cons. What are we going to cons? We're going to cons the list containing S and the car of LOS onto product of S and cooter LOS. So let's test this with this guy. So there's my AX, AY. All right, so let's walk through this first, all right, to understand what this guy's doing. So clearly this guy solves the first part of the problem, right? Make sense to everybody? Solves the first part of the problem. So what do? We have this symbol, and we want this symbol to build a list out of each symbol in here. So we're going to be building a list that immediately tells us we're going to be doing some conses. Okay? And it also implies the pattern of checking with an if, by the way, checking if we have a null list and finishing off with the empty list, because the empty list is the appropriate final step when you have a bunch of conses. Okay? So this is this pattern we've seen a bunch of times. So if we're not dealing with the empty list and we actually have to do some logic, what are we doing? We're going to build a list. And what's the list we're going to build? Well, the first list we're going to build is a list containing the symbol that we passed in along with the first element of LOS. So this will build us a list right here. That make sense? That's the constructor for list. If you want to write that in a scarier way, you could say cons S onto the cons of car LOS onto the empty list. That says the same thing. Now, why can't I say cons S onto the car of LOS? Common mistake. Why can't I do that? What is the car of LOS going to be? What kind of animal is that? Okay. Cat, dog, symbol, or list? Symbol, right? So what's the second parameter of cons have to be? A list. So car of LOS is not a list. That's a symbol. If I want to make a list out of that, I need to cons it onto the empty list. Or you can use the constructor for lists and just build a list out of these two elements. So I promise you, under the hood, this constructor for list is a lambda that has that code in it. That's what that constructor is. All right. So questions about what our current version of product does. All right. So now what's missing here is we are not going through every element of this first list. Instead, we're just giving a single symbol. What I really need to do is I need to do the same logic for each element in S needs to become a list, right? So here's something that will help you in future assignments. We can certainly, anything you could write in two functions, you could write in one function, okay, with the right level of constitution. But why not call this guy product helper? And product helper takes a single symbol and a list of symbols. This guy produces a list that looks like this. Now, if I then write a define product to be a lambda that takes in a list of symbols 1 and a list of symbols 2, and I ask the question if null list of symbols 1, return the empty list. It's a normal pattern, right? Else, and this is where things get a little sketch. Okay. Else, we might think that the correct thing to do is a cons. All right, because that's what we're used to. So let's start with that. Start with a cons. So I'm going to cons some stuff together. What am I going to cons? I'm going to cons the result of product helper, passing it the car of LOS1 and the entirety of LOS2. Okay, oh, I have an extra parenthesis here, right? So I'm going to cons that, whatever's returned by that. So this guy is going to be a single symbol, and this guy is going to be the entirety of the rest of it. Correct? So this is going to give me a list of two lists, so something that looks like this. Okay? And I'm going to cons that onto product of the cooter of LOS1 and LOS2. Something that looks like that. All right. Now, let's go ahead and let me update this guy. So this is going to be A, B, C, something like that. That was our first test case, or maybe the only test case, whatever it is. Now, what we're hoping to get out of that is a flat list that has a bunch of two lists in it. That is the two lists containing AX, another two lists containing AY, another two lists containing BX, so on and so forth. But it's a flat list, not a list containing lists of two lists. Okay, so when we use cons here, let's go ahead and run this. Oh, product of, oh, this should be the car. Product helper takes in a symbol, so car of LOS1. And we're consing that onto the product of, oh, no, this should be cooter. That's going to get the cooter of LOS1 along with the entirety of LOS2. It's a pair given a. What do you mean car expects a pair? Product helper expects a symbol. Car of LOS1 is a symbol. LOS2 is my list of symbols. That's LOS2. This would be the car of LOS1. And I'm consing that onto the product, whatever's returned by product, of the rest of LOS1 and the entirety of LOS2. Can I not cons a list onto a list? Because as it's written, this is incorrect anyways. I was trying to show you that it was going to give you something else, but 1 onto the list 2. Yeah, so that works. So what's wrong with this? The product of cdr LOS1 is going to give me a list. If that's the empty list, return the empty list. Passing it LOS2, cons. Car expects a pair given an A. Which car is that? The only car we have is this guy.
In the first one,
This one here?
in product helper, you have the product that was called as product.
Oh, I didn't fix that. I get it. My recursive call to product helper is still calling product because that guy used to be called product. All right, so notice here that we have a list containing a list of 2 lists. So while the content looks the way we want it to look, right? The output looks the way we want it to look. In the big picture, we see all the pieces that we want. The problem is that those pieces are currently kind of wrapped in some lists, right? Now, we actually do have a fix for this. I don't remember if it was homework we did in class. Didn't we do a thing called down that took a list away from a list? We did it in class. So effectively, if we could unwrap these guys in the middle, we would be stuck with our correct answer. The alternative we can do is you can use a function here called append. What append does is it glues 2 lists together as a list. So as an example here, if I do cons list 1, 2 onto the list 2, 3, if I do that as a cons, I get the list containing the list 2, 3 onto a 2 and then a 3. When really I want the list, actually I probably should have written this 3, 4 over here, but whatever. Really what I want is I want the append of the list 1, 2 onto the list 2, 3. And what this is going to give me is the flat list 1, 2, 2, 3. So it glues the 2 lists together as a resulting single list. So by making this an append, we get our flat list of 2 lists. That makes sense? Now let's see. We probably can solve this pretty awesomely with a map as well. So we have every element of the first list, and we want to map it onto the second list. Yeah, so for example, let's do this as define product map to be a lambda. Actually, let's solve the other one first, and then we'll come back and show you the map version of this, just so we have time, just in case the other one takes longer. But effectively, what we would do is we would map a symbol onto create list of these two things in that second list, giving us a new list, and then append all those together. So map would actually make this a little bit shorter, actually not substantially shorter. All right, 1, 2, 2. This is the next one. Filter in a predicate and a list. Returns the list of those elements in LST that satisfy the predicate pred. Okay, so number, remember we talked last time that things that have question marks at the end of it, naming convention typically are things called predicates. Predicates are functions that take a single parameter and return a true or a false. So we're testing, is something a number, is something a symbol, something like that. All right, and we want to, so what, it's supposed to return a list of any element in the first list that satisfies the predicate. Okay, called filter in. Find filter in to be a lambda that's going to take in a predicate and take in a, is it a list of symbols or a list of numbers? Oh, list of anything. Okay, got it. List of elements. List of elements. All right, so we have a list. And what we want to do is, as long as we still have stuff in the list, we are going to do something. So we'll ask our normal question, if null LST, go ahead and return the empty list. Otherwise, we're going to be doing some consing, but we're going to be situationally consing, right? So now we need to ask the question. If the list is not null, that means we have stuff in it. So we'll ask if, when I apply that predicate to the car of my list, if that's true, then cons the car of LST onto filter in of my predicate onto the cooter of LST. That's what I'll do if when I apply the predicate to the first element of the list, it comes back true. If it comes back false, that means I don't want the next element of the list. Correct? So in that case, I'll just call filter in pred cooter of LST. Effectively just blasting past the car because the car doesn't give me a true when I apply the predicate to it. Like that. All right. So let's test this. Let me take this product thing out here so it doesn't get mixed in. So there's my list 2.7 for this one. And then this should be A and foo. That makes sense? So that's our filter in. So now let's go back and let's do product as a map. All right. So really what we want to do is I can take, when we did this with that helper, right? I can take a single symbol and I can map it onto every element of a list. So the second parameter of map is always a list. The first parameter of map is a lambda. Okay, so and that lambda takes in a single parameter because it's going to apply that single parameter to every element in that second list. So let's go back here and we're going to write product helper call this guy product helper map. So product helper map is going to be, let me kick it down a couple lines so you can see stuff here. So product helper map is going to be a lambda that takes in a symbol as well as a list of symbols. And then what we want to do is we want to map a lambda that takes in that symbol S. And what is it going to do with it? It's going to make a list out of S and, need to map that onto, second value would be a number. So we're not going to actually do lambda. We're going to do, we'll call this, well, S is fine. It's just a different S. So let's call this, we'll call this guy sim. And we're going to make a list out of S and sim, like that. And then we'll pass it the list of symbols as a second parameter. So sim here is the parameter coming in from our list. S is the value we have up here. So let me just show this to you real quick. So if I call, let me take away these two test cases here. So we're just going to test product helper map. So I'm going to call product helper map, and this guy's going to take in that A, and let's have it take in what was it, XY? This is the second list for our test. And what we expect to happen here is we expect to get a list of two lists where the first list is AX and the second list is AY. So when we call map, S is always going to be this symbol A. But the function that we're mapping, this guy right here, creates a list out of the symbol. With the first time, the symbol will be X. The second time, the symbol will be Y. Because that's how map works. Map takes a function and applies it to every element of a list. There's the X. There's the Y. So the first time this lambda gets called, sim will be equal to X. So there's the X there. S will be equal to whatever S already was, which is the A. So this will give me the list AX. The second time it gets called, I'm going to have the list AY. So there's the list AX and the list AY using map. Okay? Now, so we can use product helper map for that. Then we actually call product. This guy down here, we can call this shorter, slightly shorter, map version of product helper. Now, can we apply this to the first thing of the list? I don't think so. I think it's about as short as we can make it. So I'm not sure that map helped us that much. Here's the difference between product helper and a map version of product helper. A little bit smoother, but probably harder to understand. This first one I think is easier to kind of walk through and get. But that is a map version of it. Go ahead.
For the map version, I did have like a shorter thing that did work.
Okay.
Like I had like the same thing you had, but like the append map, lambda. Like after all that, I then called product again and then just did the cutter of the first list.
So you did product as a map?
Yeah.
So you appended. What was the first thing you appended?
So like it was define product and the SOS1, SOS2, if null, SOS1, empty list, append map lambda S2 list, and then car.
Oh, okay. What you did is you wrote this helper as a lambda.
Yeah.
Yeah, so what she did is this. That helper, there's that symbol going to the helper. Here's the list of symbols. So what she did is she mapped onto, so So she did map a lambda that took a sim onto my, what was it, LOS2? This would have been this would have created a list out of the car of LOS1, which is equivalent to our S above, and our sim. So she's mapping that lambda onto every element of LOS2, and then she's appending that. So now product is self-contained. We don't need a helper function for this. But what do we have here? This is our helper function. Well, really this. That's the result of our helper function. So you can either write it in a named function up here, product helper map or product helper. Both of these guys do the same thing. Or, what's a lambda again? Unnamed function. So this is the identical logic. We just didn't name it. We just passed that function in each time. Make sense? All right, so there's several versions of that. All right, so let's see, what is next? So we just did 1, 2, 1, 1, 2, 2. All right, next one is list index returns the zero-base position of the first element of the list that satisfies the predicate pred. Oh, that one should be easy. Why is that 2 stars? Well, we're gonna pretend like that's a 1 star. All right, so we'll do that one. Every returns false if any element of the list fails to satisfy the predicate and returns true otherwise. So every returns true if every single thing in the list we pass it gives you a true for this predicate. That's actually an interesting one. Solutions, it'll be interesting to see what solutions we get. I can come up with 2 pretty good solutions. One of them, if you use one of them, it'll actually be very easy. But the way it's written, so this one's actually kind of a trick. And the reason it's kind of a trick is we've been talking about patterns, right? And when we're going for patterns, we've been introduced to 2 separate patterns, right? So the patterns we've been introduced to is kind of a list-based pattern and also a counting pattern. This guy looks like it's going to be a list pattern, right? My hint for this, treat this as the counting pattern. Count how many elements in there the predicate matches. And if your final count matches the number of elements that were in the original list, then every should return true. Kind of make sense? Otherwise, the alternate thing you could do is you can go through and you can, I guess the other one would be a count as well. You can go through and you can say, similar to what we did above, keep the elements that the predicate returns true from. And if you're dealing with an empty list, then every should return false. If you're dealing with, actually you would want to do the inversion of it, the empty list. Treat the number of, count the number of, or give me a list of things that the predicate, when applied to the list element, gives you a false. So it's the inverse of this guy, the filter in. This filter in gave us a list containing everything that returned true for. Change this filter in to instead give you a list of all the elements that the predicate returned false for. And if this is the empty list at the end, then it's every should return true. That means you didn't find anything in the original list for which the predicate was false. Make sense? So 2 separate ways you can solve that one. So that's filter, no, we already did filter in. That's list index, that's every Okay, yeah, these two are pretty related, and they're related to something above. So let's do 1, 2, 3, 1, 2, 4, 1, 2, 5. Is that enough? Should we do more? All right, 1, 2, 1, 2, 3, 1, 2, 4, 1, 2, 5. Oh, 1, 2, 3. Sound good? All right, I will see everybody on Monday.